So good morning again. We were talking about surface texture and surface roughnesses. So one of the parameter that we often use and a very popular number is RA. RA is basically a number that we can get from the surface. So for example, if the surface has got this roughness, and for all the values, all the data that we have, this is the mean line. If we can draw the mean line, then what we do is from this mean line we measure these heights Z, and in a simple way we can take the mean of this one. So let's say if we have Z1 plus Z2, but we will take the absolute values, not minus value. So plus Z3 plus and so on, and let's say there are n values, and then divide by the number n. So this will give us RA. So where Z is the height of the surface measured above or below the mean level, okay, and this is the line drawn such that the area of the metal above is equal to that of the valley below. So it is considered in terms of the area. So this area and this area are same. But when we do the profilometry, we do not get this area as such. So what we can take is these numbers. So all these data points we can take, and we can take a mean of that one. That will be the mean values. So now the problem with RA is that it doesn't identify the surface nature of the surface or the texture of the surface. So for example, in this here, this one, a undulating surface profile, and this one where we have got sharp peak and then this kind of valley, again sharp peak, these two have got the same RA, yeah, as it is given in the here 0.64 A is the RA value. So although they have the same RA, but they will have different tribological properties. So for example, if this is the harder surface and this hard surface has got this kind of profile or this kind of profile, they will give rise to different wear performance, because the softer material will wear out because of these sharp asperities. The contact pressure will be very, very high. Or if this material is brittle in nature, then these peaks will break off easily. Okay, so this will have different wear property than this one. Even for the lubricated case, this area may act, for example, if the lubricant is here, this area may act as a constraint here for the movement of the liquids. So therefore some hydrodynamic pressure can be created in a localized way. So this can help in the lubrication process. So this is the issue, that the actual surface profile must be considered, not just RA. So to some extent we can solve this problem. To some extent we can solve the problem of RA by taking RQ. So RQ is defined very similar to how we define RA, but here we do the squaring. We take the square of this one and then take the average and then under root here. Okay, so this will give some better picture of the number, but still RQ also has got the same issue. So here in this case, so if we have got Z1, Z2, Z3 and so on, so we will square them. Z1 square plus Z2 square plus Zn square and divide by the number n. So this we have taken the average, and now since we have squared them, we do the under root of the whole. So this will be RQ. So RQ is also called root mean square. So you can report as RA or RQ, but in many cases we just use RA. The other type of features that can be defined in this are bearing area or about bearing area. So bearing area basically defines how much percentage of the total sampling length. So total sampling length is L. How much is being in contact with the surface. So as we go in, so for example, starting here, when there is no contact, it will be 0. Just at the contact, it will be a small value. And as we go in, as we go lower and lower, we get different scenarios. So for example, here we get, when we draw a line here, all the intercepts on the asperities. So A1, A2, A3, A4, we take the sum of that divided by L, which is the sampling length, and that gives us the ratio. So this is the bearing area ratio, and this is very close to the, although this is a linear, this is for the length, but if this surface is isotropic in nature, this is very close to the area. So area will be something like this for each asperity. So this ratio is very close to the area ratio. So we can use it as area if this surface is very isotropic. That means it doesn't have any lay or any directionality. So this is another way to represent the surface. So we are just learning about what are the different ways we can represent a surface or we can define a surface, because that will have some effect in the tribological performance. So here are some typical surface roughness values of engineered surfaces. So engineered surfaces means the surfaces which has undergone some engineering process, some manufacturing. So it can be turning, machining, or casting, and so on. So all these surfaces are engineered surfaces. So for example, sand casting, flame cutting, or hot rolling. So this will give us a surface roughness or RA value. So again, you see in majority of the cases you will see RA, not other values. So RA is 12.5 to 25 micron. So this we can call it little rough surface. So, and if we want to see in micro inch, then this is the micro inch. So simply converted micrometer into micro inch. The reason why we have this micro inch in many of the books is because in America people still use imperial measurement, whereas in almost rest of the world people use the metric measurement. So in the metric measurement we call it, we use the micrometer. In imperial we use micro inch. Sawing, planing, drilling and milling. So as we see that the surface roughness is reducing for these processes, and polishing. So once we do the polishing and lapping, the surface roughness goes very, very low. So this is more represented by the polishing, 0.08. And super finishing will be 0.025. So this is the kind of surface roughness we will get. And for actual components like a gear will have 0.25 to 10. Hydrodynamic oil film bearings 0.2, 0.1. So these are the ranges. Rolling element bearing raceways will have 0.05, and rolling elements will have 0.05. So we look at these, for these components on the lower side, this is more important than the higher range, because higher range may not have very good performance. So depending upon what engineering process you have given to the surface, we can get these ranges of the roughness and the component level. These are the kinds of roughnesses we should use for these components. Here again, similar kind of data we have from another table. RA value of rough casting 10 micrometer, coarse machining 3 to 10, fine machining 1 to 3, grinding 0.2, grinding and polishing, and lapping 0.02. So it's important to remember these numbers to some extent, because sometimes you need to use those numbers, and even though you may not have the profilometer ready for use, but still you will understand just by looking at the surface that what could be the surface roughness. If you know the process it has undergone, and just by looking at the surface or feeling the surface, you can actually guess what should be the roughness of the. But of course, for precise measurement, we need to use the profilometer. So this is surface profilometer, we call it, and you might know that it works on the principle of a stylus that moves. So the stylus has got sharp tip, which is a diamond tip here, and this stylus will follow this path. Obviously this stylus cannot go deep inside, because the angle of this one may be smaller than the angle of the tip, so it cannot go, so it will just follow like this. Okay, so the profile that you get in surface profilometer is not exactly what the surface is, but very, very close. So what this is measuring is this profile, whereas the actual profile is like this. So there is a bit of error here, bit of difference here, but that's accepted. The other way of measuring surface profile is by optical method. It is also known as optical profilometer. It's also sometimes known as 3D optical profilometer. So here basically light is used, and using some interferometry, the roughness or the profile can be obtained through the optical method. So this is quite popular nowadays, because this gives a data for full area of this one quite easily. So for example, this area I want to scan for roughness, so I can measure the roughness in all of this one, and then using some software we can actually plot, and we can actually see the surface, how the surface looks like. Okay, some other parameters that can be used. One is called maximum peak to valley height. So this is basically maximum peak is here, and the maximum valley is here. So this is RY. So this will be useful in some application, for example in tolerances. When we want to know the tolerance of our manufacturing process, then we need to know this parameter. Another is known as RZ, which is called 10-point RZ, is the average distance between the 5 highest peaks and the 5 deepest valleys within the sampling length. So if the sampling length is this one, L, in this one we will measure 5 highest peaks. So here we have got P1, P2, P3, P5, and 5 deepest valleys. So these valleys and we measure these heights from a reference line, which is here, and this reference line should be parallel to the mean line, but should not be inside this roughness. It should be away from the roughness. So from here we will measure this one, P1, P2, P3. Similarly for the valleys, V1, V2, V3, 5 deepest valleys and 5 highest peaks, and then we calculate using this one. So P1 minus V1 basically gives us this height. Okay, so all the heights basically it is measuring the peak to valley height divided by 5 because we have used 5. So this gives another kind of parameter that can be used to define a surface. So Ry, which is here, Ry and Rz here. So Ry and Rz are used where extreme height of a roughness profile is important. For example, precision tolerancing or wear of a soft surface by a hard one. Another is spacing and shape parameter. So mean peak spacing SM. SM is defined as the average spacing between two successive negative crossings of the mean line. So for example, here negative crossing going this way and this way. So we measure SM1, similarly SM2. So if we go here, then we are going up and then again going down here. So SM2, so similarly SM3, 4, 5, and we can take a mean of that one. This will give us what is called mean peak spacing SM. These spacings often characterize the surfacing process, such as shot size in abrasive blasting, grit size of a grinding wheel, or feet of a cutting tool. So this has got some relation to the manufacturing process. So how we do the manufacturing. So when we do the sand blasting, for example, the sand particles will give its impression. So these are those kind of impressions. Or in grinding or during the cutting process, we use the feed rate, different feed rates. So different feed rates will give us different mean peak spacing. Now the next one is called skewness. So skewness is very, very important because this is a measure of asymmetry in the shape of the profile. So some surfaces are symmetric and some surfaces are not symmetric, asymmetric. So skewness will give us that difference. So if the surface is symmetric about a line, then this value should be 0. So if the surface is asymmetric, then this value will be either in the positive or in the negative range. So for example, if you look at this surface, if this is the center line, the mean line here, and about this mean line, this is not symmetric. This side we see lot of peaks, whereas this side, this valleys, the shape of the valley is very different from here. So therefore this one is not asymmetric. This is asymmetric surface profile, and this one gives a positive skewness. If we look at this one, here also we see that this is asymmetric because the profile here is very different from profile here. This is a sharp here, sharpness, but of course in the valleys, and this is a rounded peak here. So this one will give us a skewness which is negative. What about this one, number C? If this is the mean line, so about the mean line, is the profile asymmetric or symmetric?
Sir, asymmetric.
Why?
Because sir, that means about mean lines we have different profile in up and.
Yes, it looks like a different profile, but if you see, it has got very similarity. Above the line it is peak like this, then below the line also it is a peak, very same shape, right? It's just that this is a peak and this is a valley, but the shape is the same. So this shape and this shape, they are same. Similarly, this shape are the same. So therefore this is a symmetric about a mean line. So here the skewness RSK will be 0. What about this one, D?
This is symmetric, sir.
Yeah, this is symmetric. So this is quite easy to understand that this is also symmetric. So here also skewness will be 0. So this is the way we can understand, although there is a way to calculate the numbers, and as I said, in most of the cases we can use a software to find out the skewness of the surface. So it basically indicates about the symmetrical, whether the surface is symmetrical or asymmetrical, and whether the surface is going into the positive side or negative side. So positive side has got very sharp peaks like this one, and negative will give us more flatness. So for example, if I start with the surface like this, and let's say this is positive or 0 skewness, but after some processing or after some use, these asperities has been worn out, so now it has become flatter. So what will happen to its skewness? Will it go towards positive side more or towards negative side?
So negative side, sir.
Yeah, it will go into the negative side because now these peaks are no more there. And we have got a flatness here. So as it gets flatter, it gets into negative side. So this is how we can physically understand what is skewness. And we can understand that this kind of negative skewness is good for tribology, for lubrication, or because this provides a flat surface, the contact pressure will be low. Whereas here the contact pressure will be very large. Either this will wear out the softer surface or this itself will break and create wear debris particles. So this surface will give the opportunity for the lubricants to get filled up here, and these lubricants will move to the contact area giving mixed lubrication. So this is all good. So normally our goal should be to find out a negative skewness. So the word skew has got meaning in English also, where we use this word to mean a sudden change in direction or position, or make some biased or distorted meaning in a way that is regarded as inaccurate. So that is the meaning of skewness. But here in our engineering practice or in statistics, we use the skewness for asymmetry, so asymmetric surface. So a skewness of 0 means symmetric, and a skewness of not 0 is asymmetric, and it can be negative, positive or negative depending upon the type of surface. So skewness we can just further see. As I said just now, this surface is a normal surface which has undergone some engineering process. So A is giving this kind of profile. This one is A, but after some process, let's say wear process, some flat surfaces has been removed. So now the profile has changed and skewness has gone into negative, which is this one. Okay, and this is a distribution which I will talk about. What is this normal distribution? Okay. So this is how you will see the change in the property of the surface as we change its profile on the top. Other than skewness, you will also hear about kurtosis. Kurtosis is defined as sharpness of the profile peaks measured as the kurtosis parameter RKU. So again, this is the definition, but here we can understand from this image what it means. So this surface has got kurtosis of less than 3, and here we see that this profile is such that if we plot the distribution of the heights, okay, so for example this is the heights Z. Let's say one side is plus, one side is minus, and this is the number of times this height has happened. Okay, so this is the plot of the number of occurrence and the actual value. So you will see that this gives us some sort of flat surface, flat here. flat profile. So this flat profile is indicative of that the peaks are not very sharp, and there is a lot of flatness here. So this gives us kurtosis of less than 3. Here in this case we see that the peaks are much sharper than the earlier case here. So this gives a very typical normal distribution or Gaussian distribution, we can call it, this one, which is kurtosis of 3. And here in this example there is extremely sharp peaks. So peaks all of a sudden rise and then again goes down, again all of a sudden rise, goes down. So if we plot the z versus the number of occurrence of these data, it will give us profile something like this, which has got kurtosis of greater than 3. So if the surface has got kurtosis greater than 3, then we can assume that it has got very sharp peaks like this one. If it has got kurtosis of 3, then we can understand that this surface has got more like a normal Gaussian distribution, and if kurtosis of less than 3, then we can understand that the surface is more flatter and something like this. So effects of skewness and kurtosis is seen for tribological surfaces such as engine liners. So we can avoid the sharp peaks by keeping the skewness negative. This will avoid high contact pressure and in a localized way and less chance of wear. Kurtosis of 3 gives a broad flat distribution of the heights and valleys. Kurtosis of greater than 3 means the number of very sharp peaks is high, which is not good for tribology. And kurtosis of less than 3 would be desirable, that gives equal peaks and valleys, and the peaks have less sharpness. So immediate application of kurtosis and skewness is in the engine liners, engine cylinder liners of the IC engine. Okay, so this we have understood about skewness and kurtosis, RA and RQ, which are all important because often you will hear the values, even though in most of the engineering cases we will use only RA, but these are also important for us to understand. Another thing we should understand is about probability distribution function. So this is more like a statistical analysis, but we should understand what it means. So what is normal distribution? So whenever we have got some surface roughness like this, and we measure the data. So for example, let's say heights we will measure from some value, so or some mean, from mean we will measure the heights, right? So we will get some different values and we have to plot them. So let's say, so for example, surface heights we have got on the positive side and negative side, and here we have got the values, each how many number of values we have. Okay, although it is presented in the form of probability rather than actual number, but if you imagine if we plot in actual number, and it is, you can we can model it very easily with the class performance. So for example, we have got the grades when we give. Of course this class is quite small, but if the class has a very large number, let's say 100 or more than 100 students, and you will see that B, for example, B has got some range of marks, right? And let's say B minus, C plus, and so on. And here on this side, let's say we have got B plus. Again, we can make the range. We can give A minus, A, or even A plus. Okay, so if we do this for a very large class, the distribution of the grades, and we plot the number, how many B plus, how many B, and let's say this is very large class, so let's say this is 120, and you will see that it falls into a distribution like this, okay, which is, let's say I will add a plus 2, okay, which will be this one. I will add C minus, and even D and E, and you will see like this. So what will happen is it will follow a curve like this. You understand this one? So
Yes, sir.
yeah, for a large class, I'm just plotting their grades and how many students scored that grade. So how many students scored B plus, B minus, C plus, and on this side, and it will fall in a normal distribution for a large class. I'm not talking about small class like 5 or 10, but at least you need more than 100 students, and they will follow this curve. This is also known as bell curve, because this looks like a bell. So either we call it bell curve, or we call it normal distribution, or we also call it Gaussian. So this is the understanding of what is a normal distribution. So when you have got a very large samples, let's say population sample, and your let's say salary of people in a very large population, 2,000 or 3,000 people, and if you see the curve, it will curve like a bell. That means majority of the people are here and very few people are here. In this class means majority of people are performing in the middle range, like average, little more than average, less than average, and very few people are performing very high grades like A plus, and also very few people are actually performing poorly as well. So not everybody is performing poorly. So this gives us the normal distribution, and it happens for many types of application, and also for our surface application. So here that is the way it has been made, but here it is more like a probability distribution function, not the actual data, but the meaning is the same. In many of the engineering surfaces, we would expect this kind of surface. For example, if surface was created because of some wear process, some erosion process, bead blasting or shot blasting. So this kind of processes will create exactly normal distribution, but some other processes like machining and grinding may not give you a normal distribution. It may have some different values because it has got some lay or some anisotropic in nature. So that is the meaning of normal distribution. I think what we should understand is that under what situation we can get normal distribution, and under what situation we will not get normal distribution of the surface. Another one, another parameter, which is the last one, is called standard deviation. Standard deviation, you must have heard many times about when you have got some data, you want to calculate the standard deviation. That means it gives you the scatter. So for definition, we can say standard deviation is a measure of the amount of variation of a set of values. So you have got a set of values in the form of surface roughness or in the form of any other data. So you want to know the amount of variation, how much the values are varying from a mean value. So low SD means the values are close to the mean. High SD means wider scatter about the mean. Okay, so this is the meaning of standard deviation. So standard deviation is calculated like this. So the data you have got minus the mean squared. So similarly you do for all the data, sum them up, divide by number of data you have got, n, and then you do the under root, and you see that this definition is same as RMS, root mean square, or RQ. The definition is the same. So In fact, standard deviation and root mean square RQ are the same. So where xi are the given data, mu is the mean of the given data, and n is the number of the given data, RQ is equal to sigma or standard deviation. So for Gaussian distribution, just now we talked about normal distribution and which is also known as Gaussian distribution. RQ over RA will be 1.25. So can we do a small exercise now? I will give you some values. Do you have got a calculator with you?
It's a mobile calculator.
Okay, you can use the mobile, yes. So let's say I found out some data of whatever, it can be friction, wear, or it can be surface profile, and I have got these numbers. Once I measured 3, the next time I measured 3.1, another time I measured 2.9, 2.85, and then I measured 3.15. So I did 1, 2, 3, 4, 5 readings, and in the 5 readings I got these values. So now can we find out the standard deviation of this one?
Yes, sir. So its mean is 3.
Okay. So it gives mu mean as 3. Okay.
Hello, sir. Hello.
Yeah. Go on.
Its mean is, sir, is 3.
Yeah, mean is 3. I have recorded it. So. And then you have to calculate sigma, the standard deviation.
Yes. I'm just calculating. So 0.114.
Okay, 0.114. And so this should be same as RQ, right? Because definition is same. And
Yes,
can you calculate RA? Just now we talked about RA. You can go back to that.
RA, sir, is 3, no? Because we have to take mean of this. RA is 3.
RA cannot be 3. You take the.
Okay, first we have to find center line, no, sir?
The 3 represents the center line. Now from center line, how much variations for each data you are getting?
Yes, sir, yes.
That is a Z1, Z2, Z3.
So RA is 0.1.
RA is 0.1. Okay, so just for these 5 data points, we can find out the standard deviation, RQ and RA. Here if I do the ratio of RQ over RA, it will be 1.14, right?
Yes, sir.
So for Gaussian distribution it was 1.25, but this one, that means this is not Gaussian distribution. So this is all the types of surface features or textures. So when we talk about texture of a surface, we include many information, not just RA or RQ. Okay. So that is how we define the surface texture. But in majority of our cases, we will use RA as the parameter, and sometimes it is possible to use just one parameter like RA if the manufacturing process the surface has gone through is the same. So in that case, whatever variation will be the same in the 2 surfaces, so we can use RA as the number. So in engineering drawing, you will see that surface texture symbols. So I thought of including this so that we understand how surface textures are defined in our engineering drawing. So generally this symbol is used for texture, this check symbol. Okay, and so this is the basic surface texture symbol. Surface may be produced by any method except when the bar or circle is used. So this means any surface method is fine, but if we use this one, a bar on top, so this is the check, original check, and this bar, so material removal by machining is required. So the horizontal bar indicates that material removal by machining is required to produce the surface, and material must be provided for that purpose. So that means material removal by machining. And if this flat surface width is cross means here the value will be given. The value in millimeters for x defines the minimum material removal requirement. So this defines how much material removal has to take place. And if it is a circle like this, in this check, the material removal prohibited. So no material removal should be done, no machining should be done. The circle in the V indicates that the surface must be produced by processes such as casting, forging, hot finishing, cold finishing, die casting, powder metallurgy, or injection molding without subsequent removal of the material. So this is the symbol, a circle inside this V of this check. And further, more data can be given. In that case, this check symbol is given a horizontal line like this. So surface texture symbol to be used when any surface texture values, production method, treatment, coating, or other text are specified above the horizontal line. So above the horizontal line something will be specified, and here you can see that more explanation. So for example, here if A is here, so A is the roughness value, RA in micrometers, B production method, treatment, coatings, other text or note. So here you can use some text. This is number. C is the roughness cutoff or sampling length in millimeters, direction of lay, and so on. E, minimum material removal requirement in millimeters. So this is how the surface texture symbols are used in our engineering drawings. So it is important for us to remember them, because sometimes when you see an engineering drawing and you will see this kind of symbols and you will be confused what do they mean. So a little bit going further, contact between surfaces. So now we are talking about two surfaces when they are contacting with each other. So a surface can be represented like this, another surface can be represented like this, or it can be flat, it can be sharp, and whatever. There are many ways we can represent. So when two surfaces come in contact, they will always come in contact with certain load will be there, and the geometry will be there here, and also we will have the information about the material themselves, whether the material is still in the elastic range or it has gone into plastic range. So these information we will try to find out, and then our job is to find out the contact area, because we have learned that contact area is very, very important. And the contact area, the actual contact area is not same as the apparent contact area. For example, here in these two contacting surfaces, the apparent contact area is this one. Okay, but actual contact areas are only these, some of these. So this is the actual contact area, but apparent contact area, of course you add this another dimension because we are looking at only the cross section. So actual contact area is this, the apparent contact area is this one. So apparent contact area is very, very large, and it is not very useful. What is useful is the actual contact area. So how to find out actual contact area? Can we measure actual contact area?
Yes, sir. We have tools for that, sir.
Okay, but if I give you two steel blocks of steel, and then I tell you, can you measure actual contact area?
No, sir. That time when both are in contact, that time
Yeah,
we cannot measure.
yeah. But under what situation you can measure? So perhaps you can measure if one is transparent, right?
Yes, yes.
So that from the other side you can use the optical method to measure, or sometimes you can use some other coloring method. For example, some coloring has been provided, and then after compressing you know where they were touching, so you can do that. Okay, so those are approximate methods, can give you some data, but here we have got a more analytical method. And for this method we use what is known as Hertzian contact method or Hertzian contact radius. So basically these kind of asperities are modeled as a sphere on a flat surface, and this is quite valid because in most of the engineering application the asperities won't be extremely sharp like this. It will be some sort of a curved. So if you look at the asperity at very microscopic scale, you will find that it looks like this. So as we were talking about, when we see the surface profile using optical method or stylus method, it will plot something like this. And it looks like this because the scales, this scale and this scale are not same. This scale has been compressed and this has been extended. So that's why it looks like this sharp. But if I use the same scale, the same Z and the X scale, then this same surface will look something like this. Okay, so this kind of observation we should note, and we should understand that whenever we are looking at the surface profile data, it has been compressed in this length scale and extended in the vertical scale. So that's why it looks like this. But the actual surfaces will be somewhat flattened like this, and therefore we can use this as a model. We can say that the tip of the asperity is like a sphere, spherical or semi-spherical, and the other surface can be semi-spherical like this, or it can be flat. So if you use this one and you assume that these two surfaces are still in elastic contact, then the Hertzian contact radius is given by this equation, where the radius r is equal to W, which is the load applied. Of course there has to be some load, otherwise there won't be any contact area, and r is the radius of the spherical asperity. So this r is basically calculated in this case because one surface is flat, so therefore r is just the radius of the curvature of this asperity. But if there are two curved surfaces, then r has got some different definition. And E star, this one, is a composite elastic modulus because there are two materials involved, material 1 and material 2, which is, so this is given by this equation where Poisson's ratio of material 1 and elastic modulus of material 1 and Poisson's ratio of material 2, elastic modulus of material 2, both are used to calculate E star or the composite elastic modulus, which we will input here. In most of the cases we use this definition, but for the roller bearing, so ball on the raceway, sorry, in the ball bearing case, this number is used as 2 rather than 1. Okay, but in most of the cases we will use this equation. So if we use, so we can find out E star, we know R, we know W, so we can find out the contact radius. So this is how we can find out the contact radius, and the contact area will be given like this, pi r square. So this is a very convenient method of analytically calculating the contact area between two surfaces, the actual contact area, not the apparent, the actual contact area. And now we can see that the contact area is proportional to W to the power 2 by 3. There is a proportionality, and this is the actual equation. So this I want
So
to,
it should be,
yeah.
so it should be E star, no? So only E is written there in A. in A, sir.
Yeah, you are right. This should be E star because we are using this equation. Yes.
Yes.
Yeah, so my purpose was just to introduce this part, and we will go further on this one, contact between surfaces. Again, this is very extremely important for tribological systems design because we need to understand the surfaces, their texture, and then what will be the contact situation, the contact area, and what sort of adhesion, what sort of interactions are going on. So these all will help us in designing the surfaces and designing the basically tribological surfaces.